So today we're going to be talking, my name is Miguel Morales from Lawrence Livermore National Labs. Today we're going to be talking about molecular calculations. Tomorrow Luke is going to be talking about solid state calculations. So the lecture is a little bit of a combination of a little bit of quantum chemistry. Sorry, I can go there. So I'm going to first start with some basics, a little bit about philosophical discussion about QMC and a little bit of the benefits versus disadvantages of the methods. Then I'm going to be talking a little bit about trial wave functions as I'm going to try to explain the power of the method really relies on the ability to use very complicated trial wave functions, and mostly based on molecular calculations. So this would be using basis sets, typically used in quantum chemistry, and aiming at finite systems without periodic boundary conditions. Tomorrow, Luke is going to be talking about periodic systems, where in that case, we typically use plane wave calculations, and we consider periodic boundary conditions and infinite systems. So of course, most of the trial wave functions that we use rely somewhat heavily on quantum chemistry methods. So in quantum chemistry, you can do different levels of calculations that give you a lot of information already about the system, and we use as much of that information in the QMC calculations. And then I'm going to finish with a little bit of a survey about recent calculations to give you a feeling of the type of things that can be done. So the lecture today is split in two. I think we stop at 10:45, and then we have another hour. So roughly, I'll keep going until 10:45, and then we just pick it up from there at 11. OK, this is my own view, so take it for what it's worth. From my point of view, the Schrödinger equation contains all the information that we should need to solve problems involving electrons and ions. Basically, anything bigger than an atom, any collection of atoms, in principle, can be solved by the Schrödinger equation. Of course, the Schrödinger equation is extremely complicated, too complicated to even think about a realistic exact solution for a generic system. So the entire approach, the entire hope, I guess, of computational physicists and chemists is to find approximate solutions to the Schrödinger equation that can give us the information that we are interested in. But in principle, and this is a little bit ambitious, but of course, in principle, all of chemistry is encompassed in the Schrödinger equation. Plasma physics, optical, transport properties, thermodynamics, exotic phases, superconductivity, everything in some way is encapsulated by this simple equation. In practice, solving the Schrödinger equation is too hard, so we, of course, need to develop a well-defined set of approximations. The most universal approximation that's typically employed when we are studying systems in chemistry and physics is the Born-Oppenheimer approximation. Most of the theory and the simulation work depends on it in many ways. So the Born-Oppenheimer is a very simple concept. If we start with the Schrödinger equation, the Hamiltonian, of course, contains electronic kinetic energy and ionic kinetic energy. So usually small caps are meant to represent electrons, and big capital letters are meant to represent ions. So you have your electron-electron interaction, your electron-ion interaction, and your ion-ion interaction. But of course, the mass of the electron is many, many times, about 1,000 times smaller than the mass of the ions, at least 1,000 times. So if you think about it, the electrons are much, much faster than the ions. So from the point of view of an ion, an electron is effectively relaxed from the point of view of the ion. And from the point of view of the electron, the ions barely move at all. They have plenty of time to relax to the ground state while the ions are moving around. So the Born-Oppenheimer approximation, in very simple terms, is the idea that you have a time-scale separation. You solve the electronic problem in the presence of a certain configuration of ions, and then you move the ions around in the ground state or in some electronic state of the electrons. So to make that a little bit more concrete, the actual approximation basically assumes that you can separate the electronic and the ionic contribution of the wave function into two pieces like this. So for every ionic position, you have a full set of electronic states And so effectively, once you do this, you can show that you can separate the Schrodinger equation into two pieces. Of course, there is an approximation, but it relies on the fact that the mass of the electron is much smaller than the mass of the ion. And the terms that you have to neglect are typically quite small. But effectively, this allows you to separate the Schrodinger equation into two semi-independent equations. You have the equation for the electrons. In this case, you have electronic kinetic energy. You have the electron-electron interaction and the electron-ion interaction, which of course depends on the coordinates of the ions. But it only depends on the coordinates of the ions parametrically. They are just represent the location of the potential. They're not dynamical variables. And so this gives you this is called the electronic Schrodinger equation by some people, and this gives you the set of electronic states for that particular position of the ions. And once you can, and of course the energy as a function of the positions of the ions. So if you think about it, this equation now represents a potential energy surface if you collect the remaining terms on the other equation, where you now have a kinetic energy of the ions, ion-ion interaction, and the electronic von Oppenheimer energy, which is nothing else as, now you can solve the ionic problem, where now the electronic von Oppenheimer energy, which is a function of the ionic coordinates, comes from the solution of the electronic equation. And this is just a normal equation for the ions. There's a lot of benefits about doing this. If you think about it, the electrons are inherently quantum objects, but the ions are not necessarily so quantum mechanical. So this allows you to separate, to apply different approximations to this problem. And this also allows you to solve the problems completely independently. Well, it's not completely independently because, of course, you need the von Oppenheimer energy to solve the ionic problem. But to some degree, you can treat them as independent problems. And so typically, we have to do very high-level sophisticated methods to solve the electronic Schrodinger equation, but the ionic Schrodinger equation can be solved by molecular dynamics, for example. So this is the ab initio molecular dynamics, for example, method relies on doing some method to solve this, like DFT, and then doing molecular dynamics based on the potential energy surface, for example, of the DFT solution. Today, we are going to focus exclusively on solving this equation with quantum Monte Carlo methods. And of course, the assumption is that in the future, once you have this solution, you can then look at ionic problems with it. First principles electronic structure theory it basically relies on what I just described. The idea is, the first principle comes from the idea of, we try to solve the electronic Schrodinger equation with some many-body method, and then use that solution to look into ions. There are three typical ways to think about solutions to the Schrodinger equation. The most used, arguably the most important, is density functional theory. The big benefit of density functional theory is that it gives you a fairly high ratio of, if you think about accuracy with respect to computational time. From the point of view of solving the Schrodinger equation, it actually gives you a fairly accurate solution, and the cost is not high. It scales well. It usually scales as n cubed, but there are order n methods, so you can do very, very large systems. And it's easy to parallelize. There are very well-developed codes. You can take typically your favorite electronic structure code, hit enter, and you get very good solutions. The problem with density functional theory is that it's very hard to improve. It is, at the end of the day, a mean field approximation. At least that's the way I see it. And so once you make a certain approximation for what the functional is, there is very little you can do to improve it. There's no systematic way of getting better answers within DFT. So you get what you pay for in some sense. The accuracy is technically unknown. You have to have some idea of what the actual answer is to be able to judge how well DFT is doing. And it fails if electronic correlation is important. This is important. This is well known, and it's important. At the end of the day, it's mean field. So if electron correlation dominates the problem, it has to fail. If you are a chemist, then of course in chemistry, quantum chemistry methods have always been the standard. In this case, they are extremely accurate. They are extremely robust. You actually attempt to solve the Schrodinger equation directly. There are very well-developed codes. There are some of the benefits. The negative is, of course, the cost is extremely high. So the cheapest wave function method in quantum chemistry is MP2, and that is n to the 5. If you want to do couple clusters, n to the 6, parentheses this, n to the 7, and so forth. So that means that it's very hard to do solids. It's almost impossible, although now you can do a little bit of work within solids. The theory is extremely complicated, so you are not going to understand these methods by just spending a few hours looking at them. And it's very hard to do high-performance computing on these methods. So you typically can only work with a handful of cores. This is starting to change, but for the most part, the more sophisticated methods are really hard to parallelize. So of course, we have quantum Monte Carlo as a third alternative, which is what we're talking about in this tutorial. It's very accurate. It's quite close in accuracy to quantum chemistry methods. It's systematically improvable, so you can get, if you have more computing time, you can get a systematically improvable answer. And it's trivially parallelizable. The scaling is not bad. The scaling is n cubed, so it scales roughly close to DFT. And again, it's trivially parallelizable. If you give me a machine that's 10 times larger, I can use that machine without any real issues. The negative side, of course, there's a negative to everything. There's a high cost. It's n cubed, but the prefactor is large. So from the point of view of wild clock time, you're going to be spending CPU time. That's no question. It's human time intensive. As opposed to the other competitors, you have to know a little bit more about how to use the code to be able to get correct solutions. This is, of course, changing with time, and hopefully our goal within QMC-PAC is that we get the same level of robustness and friendly userness that you get within other codes. But right now, if you have a complicated problem, you need to know a little bit about how to use the code. For simple problems, then the code works just fine without knowing all the details. The community is small, of course. There are not that many groups. We are probably 100 times smaller than either of these two communities, so progress is not as fast, to be honest. And there are some issues with systems at very, very high C. Again, we're working at those issues, and they should systematically go away. But as of right now, if you want to do really, really heavy calculations, there are some, you have to be careful in how you do them. OK, so why QMC? So if you think about it, and this is something that I've always heard David say, if you have a classical problem, if you are solving a problem of a simulation of ions, you know the ionic interaction, there is no question. Stochastic methods are the way to solve exactly classical systems without antisymmetric symmetry. So bosons, to be exact. So if you have a problem of bosons, stochastic methods just give you the exact solution. The goal, I guess the dream of the QMC community is that we can build a method that would be equally reliable, equally accurate, basically exact for any type of problems, whether it's bosonic or fermionic. So some of the strengths of the method is the fact that it deals directly with the many-body Hamiltonian. There are no approximations to the Hamiltonian. There is no empiricism. So you get effectively a direct treatment of electronics correlation. It's not like when we were doing the FT, you have to make a guess about what correlation is. And so you get a lot of issues with self-interaction and cancellation of errors and stuff like that. In QMC, no. In QMC, we have the exact Hamiltonian, and that's what we're working with. The scaling with particle number is low. So we can do QMC calculations on thousands of atoms. You need supercomputing power, but you can do it. And it's very efficiently. We can run on the largest machine. So this, you can tell that these lights are old because I have 250,000 CPUs. This is more like 1.5 million now. So we can use an arbitrarily large machine with very high efficiency. On the weakness side, so the fact that you are doing the many-body problem directly is actually a strength and a weakness too. That means that we cannot simplify the problem. If you do calculations in quantum chemistry, you can play with your basis set. You can play with many things to make the problem simpler and not have to deal with the full-blown Hamiltonian. In QMC, we don't have so much luxury. We are always working directly with the many-body problem, and it's hard to simplify. And the only approximation, well, one of the two approximations, we're going to go into some detail about that later, which is a fixed node approximation. It's hard to control. It's systematically improvable, but it's hard to control. And there's a fairly high learning curve, as you'll probably realize this week. There's quite a bit to learn to become an expert in these methods. Anyway, so now turning into an actual calculation with QMC, specifically with QMC pack, this is what a simple molecular calculation looks like. What I'm trying to convey here is the fact that the code has evolved to the point that running molecular calculations is completely trivial. If the system is simple enough that you don't need to go and tune any of the parameters in the optimization, then you can go from an input file in games, for example, to results in QMC with 5 simple steps. And this is what they look like. First of all, you start with the quantum chemistry calculation for molecules, of course, and there are different codes that you can use. I tend to use games as the code in the examples, but you can also use MoPro or Gaussian, or if you have your favorite code and you really think that this code offers something that the entire community can benefit from, so we can probably write a converter for arbitrary codes fairly quickly. We do need somehow community encouragement, let me put it that way. But otherwise, let's say you can just take games. If you know how to write input files to games, then you can do QMC calculations very straightforwardly. So you can do, for example, a DFT calculation with games, get the orbit, and then the idea is we would get the orbitals from games to write the initial trial wave function calculation, and then optimize all the parameters within QMC. So from the point of view of the user, you just execute games with an input file. You have to know how to write input files for games, of course. There's a single call that takes the output from games and converts that into the input that QMC pack needs. And you can tell that these are all slides because now it's not called QMC app anymore. Now it's called QMC pack, the executable. We recently changed it. But anyway, so you go from this conversion generates all the input that you need except a handful of XML blocks, which I'm going to describe later. So then after you do this step takes a second or two. This is very quick. You run your optimization calculation, which is what I described yesterday with QMC. And this will generate an optimized wave function that then you can use to do VMC and DMC calculations. And when you're done, you use QMCA to do statistical analysis on the VMC and DMC calculations that you just generated. So with these 5 simple steps, and of course an input file from games, you can effectively do a molecular calculation. So as I say, the converter basically takes care of all the work for you. You don't really have to think too much about it. You do need things like an effective core potential if you are going to use one, and you need to know about basis functions, and you need to have your favorite basis set. But this is all effectively relevant at this level. The converter takes care of translating all of that for you. I just mentioned effective core potentials. So if you're a physicist, you would call this pseudopotential or PAW or your favorite approximation for the core. If you're a chemist, then it's typically effective core potential, but they're the same thing. Basically, the idea is that we have core electrons that are not really chemically relevant. And they, on the other hand, have a very high computational expense if you want to do them directly. So we remove them and we replace them by an effective core potential that takes care of reproducing their influence on the problem. This is, of course, an entire field. This is not directly a Monte Carlo topic. This is given given a choice of effective core potential, QMC would work on top of it. So I mean, it would be an entire seminar series to understand effective core potentials in detail. Tomorrow, Luke is going to talk a little bit more about that and about the different, how to be careful when you do use effective core potentials in QMC calculations. So for today, I'm just simply going to say that for most calculations, we actually don't use the Coulomb interaction directly between electrons and ions. We just replace that with an ECP. And so the ECP has a local part. Local part means that it just depends, it's a one-dimensional function, and it's spherically symmetric. And then you also have a non-local piece where you decompose it in different angular channels. This is all completely standard and taken from the quantum chemistry community. You typically expand this on Gaussians because, of course, chemists like to work with Gaussians. It's very easy to generate the different matrix elements with Gaussians. So basically, it's almost universal in the quantum chemistry community. And once you choose an ECP, then of course you typically want to use a basis set that has been tailored for that particular effective core potential. Within the QMC community, there are two well-known sets of pseudopotentials where you can pretty much go and grab a pseudopotential for one of these test sets if you're doing chemistry calculations. For solids, it's a little bit more delicate, and Luke is going to be talking about that tomorrow. But for example, there is the Burkatski-Filippi-Dolg set of pseudopotentials. This is the web page where you can access them, and you just click on any element. Then you choose the corresponding basis set, and that gives you the input that you would need to just click and drop in the game's input file, for example. Or you can also use the Casino set of pseudopotentials, which can be accessed, I believe, still through this web page. And it's the same. You just click on the element and get the information that you need and put it on the input file. We started distributing these pseudopotentials now within the QMC pack distribution. For sure, the BFD ones, possibly in the future, the Casino ones, but certainly the BFD ones, which are probably the ones that people use the most. So now you can download them all, basically, and just put them anywhere and use them without really having to go to the web page. If you want to know more details about how to get them, then you can ask Paul or ask any of us. But effectively, it's in the SVN server now. So trial wave functions. Yesterday, we talked a little bit about optimization, and we talked about, in a fairly abstract way, we talked about the requirements that we need to do optimization of the wave functions. So if you remember, if you want to do VMC and DMC calculations, if you remember David's lectures, you need to know how to evaluate the wave function. You need to know how to evaluate the gradient and the second order and the diagonal of the Hessian. Basically, the second order derivative, the Laplacian of the wave function. If you want to do optimization, then in addition to this, you also need to know how to evaluate the gradient with respect to any arbitrary variation or parameter of the same three quantities. So a QMC calculation, basically, especially if you're doing optimization, you have to be able, any wave function that you can evaluate these six quantities, you can use within QMC. This is very important, of course. The accuracy of the method is ultimately controlled by the type of wave function and the quality of the wave function. The efficiency is also controlled by the quality of the wave function. So we want to think about what wave function we want to use somewhat carefully, depending on the problem that you have. And of course, as I have said many times, QMC can handle anything that you can evaluate in real space, basically. So in chemistry, the most important decision is typically the basis set. Well, it's quite important. What is a basis set? So we are going to be working with n-dimensional wave functions of electrons. But those n-dimensional wave functions are always expanded in a set of single particle orbitals. So this is the orbital of one electron. And so that orbital, which is an abstract concept, I mean, it's a generic concept in principle, has to be expanded in some practical way. So what in the chemistry community and for molecules, the universal way is to expand it in terms of a basis set that's atom-centered. So every atom has a set of basis functions associated to it, and a final orbital is a linear combination of all the basis functions in all the atoms. So it's just a simple sum where I think, I index the ions, and mu index the different basis functions on each atom. So each different species has its own basis set, and so the collection of all of these things is what we call the atomic basis set, because it's the native basis set. And the single particle orbitals is what is the collection of electronic orbitals that is expanded on the atomic orbital set. So there are two standard basis sets that are used. Slater type orbitals are what we should really be using in practice because they have the right shape when you get close to the nucleus, but they are hard to use within a quantum chemistry framework. Calculating matrix elements of the Coulomb operator between Slater type orbitals is non-trivial. So chemists have decided collectively to use Gaussian-type orbitals because you can do the integrals analytically. And so effectively, this improves the speed and the efficiency of the codes dramatically. The problem is the Gaussians don't really have the right shape when you're close to the nuclei. So a typical basis function is a collection of multiple Gaussians done in such a way that you can reproduce the behavior of the orbital close to the nuclei. And so in practice, and this is if you go inside the code, you can write the GT. So the code in the QMC side, I should say, it doesn't care. It can use Slater-type orbitals, Gaussian-type orbitals, numerical orbitals. It's somewhat of an irrelevant point from the QMC. But since we are reading information from quantum chemistry, then it does matter how you do the quantum chemistry calculation. And you can do the Gaussians, which are going to be the things that we are going to use, and most likely you are going to be using today, in two different ways. You have always a radial function, so you have a radial function and an angular function. In the case of spherical ones, you use YLMs, and in the case of Cartesian, you just have powers, a polynomial expansion of XYZ. Again, QMC pack can use either. It really depends on what your chemistry calculation is using. In practice, once you go into QMC, we actually transform the radial functions in either one to a numerical grid, and we do spline interpolation. So it doesn't really matter where you start from. That's what I meant. At the end of the day, it's actually going to be used in a numerical basis internally in QMC because it's much more efficient. You don't want to be evaluating exponentials when you can just do spline interpolation. OK. If you're a chemist, I'm sorry. This is all very boring to you. I guess I just have to be... I have to make this a little bit generic. So considerable effort has been put on the chemistry side because, of course, the choice of basis is an extremely delicate problem in chemistry. The answers that you get are only as good as the basis set that you use. So they have done an excellent job in building families of basis sets that are systematically convergent. So typically, if you're familiar with this, you name them by the highest angular momentum in the basis. So for example, correlation consistent basis sets of Dunning are very popular. And you can show they were built with the idea that if you do a correlated calculation, every time you increase the cardinal number of the basis set, you have a logarithmic reduction. You have a systematic reduction of the error, which I believe is logarithmic. So if you go from double, triple, quadruple, quintuple zeta, you can see that the error in your calculation is going to 0. And of course, the error is defined as the difference between the finite basis set and the infinite basis set limit. So in QMC, the dependence with basis set is much smaller, but there is always some residual amount of basis set. We typically don't have this type of magnitude of errors. They're way, way smaller than this. So we usually can use triple, double, triple, quadruple zeta, depending on how careful you want to be on your calculation. Of course, in chemistry calculations, you have to always do some sort of extrapolation to the infinite basis set limit because the convergence on basis set is so slow. So you always have to rely on some sort of fitting or extrapolation approach. In QMC, we rarely rely on any of this. So in practice, if you want to do a QMC calculation of molecules, the first thing that you do is you go to your repository and you choose an ECP. Then given that ECP, you make a choice about which basis set you want to use. So ECPs almost universally come with an associated basis set. So the only typical decision they have to make is whether I do triple zeta, quadruple zeta, quintuple zeta, and so forth. So usually, if you don't have any experience doing this, then the best choice is to do calculations with different basis sets and see how the energy converges. Once you develop intuition and you know how to do things, then you can just make choices, and they're almost always good. It's rarely you get surprises when you do these things. If you remember yesterday, and I probably should have had this, the wave function is always written in terms of an antisymmetric piece and a Jastrow correlator. So the antisymmetric piece is usually written in terms of Slater determinants. Of course, this is not the only choice, but it's the standard one, is the thing that most people use. A Slater determinant is nothing else than the determinant of a matrix, where the matrix has, single particle orbitals in one index, in one side, and let me say, yeah. So you have single particle orbitals in one axis, and then electronic coordinates in the other. And so you take the determinant of this matrix, and that gives you the determinantal piece. As I mentioned before, you need to know how to calculate the gradient and the Laplacian of the wave function. So these are simple formulas. You can show that the only thing that you need is the inverse of this matrix and the gradient and Laplacian of the individual basis functions. And you can calculate the gradients and the Laplacians of the determinants this way. Of course, you don't need, typically you do calculations with a single determinant, but you can use as many determinants as you want. There's nothing stopping you. The standard way of doing multi-determinant calculations is in addition to taking the Hartree-Fock determinant, which is the determinant where you occupy all the lowest single particle states of your theory, you can also include determinants where you include an excited orbital, an excited single particle orbitals, 2 excitations, 3 excitations, and so forth. And you can show that if you include enough of these things, or in the limit you include them all, you have reached the exact solution of the problem. This is a basis in many body space. In practice, if you think about quantum chemistry methods, you need millions and millions of these determinants to capture correlation energy accurately. In QMC, all we're doing is improving the trial wave function near the nodes. So we typically only need hundreds of these determinants in the harder calculations to really get very, very accurate solutions. So we do use the determinants coming from chemistry, but it's on a completely different scale, typically hundreds. Okay. So I think I just described really what configuration interaction is. So since we're going to use some quantum chemistry methods to generate trial wave functions for our calculations, I'm going to do a very brief description of some of these ideas. If you're a quantum chemist, I'm sorry. If you're not, then you're welcome to ask any questions. So these are the calculations that we will be doing with games, for example, to then generate the input trial wave function for QMC. So configuration interaction is a very simple idea. If you're a physicist, you call this exact diagonalization. If you're a chemist, you call it CI. And it's the idea that, again, as I mentioned before, if you consider all possible single, double, triple, and so forth excitations outside your Hartree-Fock determinant, effectively, this is a complete basis for the many-body problem. This is a complete basis in Hilbert space. So if you diagonalize your Hamiltonian on the space of all of these determinants, then you have the exact solution of the problem for the particular basis set that you're using. Of course, if you think about it, this is a combinatorially large problem. So the actual number of these determinants is impossibly large in practice, which is why full CI is rarely used in practice. But in principle, you can, like I mentioned, you can expand the wave function in these determinants. And again, the number is combinatorial in the total number of states in your basis function. And once you do this, you can show that an eigenvalue equation gives you the solutions that you need if you write down the matrix elements of the Hamiltonian between 2 arbitrary Slater determinants. In practice, this is rarely used because it's way too expensive, so you do truncated CI. And truncated CI means that you consider all excitations up to a certain point. So CI singles, for example, is the Hartree-Fock determinant and all single excitations outside the Hartree-Fock determinant. CI singles doubles is the same, now including double excitations too. And you can keep going until you feel that you have done enough, and you truncate your excitations, your determinant excitation spectrum at some point, and then you go and you solve this equation with the limited set of determinants. The problem is it's not size extensive. This means that if you make the system larger and larger, the only way you can keep the accuracy homogeneous is by increasing the number of excitations. So if I double the system size, I have to double the type of excitations that I allow. Otherwise, the amount of correlation that I extract back decreases with system size. So if you do CI singles doubles, for example, in the thermodynamic limit, you're not getting any amount of correlation, which is why it's something that's used in chemistry, but it's not so popular, to be honest. Then there is, we're going to be doing some truncated CI calculations in the tutorials to generate input trial wave functions for QMC. We'll also be doing what's called complete active space CI, which is the generalization of this idea, but we only include excitations within a subset of the orbitals. So in a CAS calculation, you divide your spectrum into 3 pieces. I believe that I explained this better. Sorry. No, so it's not here. Sorry. So you divide your calculation into 3 pieces. Let's say that this is my entire spectrum. I only take a subset of the lower single particle orbitals, and I consider all excitations, single, double, triple, as many as I can do, but only on a subset of the orbitals. So this is equivalent this is equivalent to solving the full CI problem, but on a limited set of states, not on the entire basis set. And you can show that the amount, the stronger part of correlation always lives very close to the HOMO-LUMO gap. So this allows you to get a description of what's called strong correlation, but it doesn't have the weaker correlation that comes from this summation of very small contributions, but a combinatorially large amount of them coming from all the high-end states in the basis. So we're going to be doing also some CAS. This is typically called CAS SEF if you do it self-consistently, or CAS CI if you don't do it self-consistently. We're going to be using this method also to generate input wave functions for QMC. In summary, basically, typically you can use CI methods to generate multi-determinant wave functions, which very successfully allow us to reduce the fixed node error in QMC calculations. If you're doing molecules, this is something that you probably should know if you want to get the highest possible accuracy that you can get with QMC. I guess, I mean, I wanted to have a little bit of a discussion about the distinction between strong and static and dynamic correlation. This is a complicated subject, so maybe we can have a discussion if you don't agree with me, and not everybody completely agrees with this, but especially in the chemistry community, this is something that's debated to some degree. But effectively, if you think about correlation, there are 2 types of correlations, and you can think about these types of correlation from the point of view of CI. So if I do my CI expansion, let's say that I have 1 billion determinants in my CI expansion, and you go through the billion determinants and you look at the coefficient of each one of these determinants, let's say that you separate them between the very large coefficients and the very small coefficients. Static correlation or strong correlation is this idea that in a problem, you typically have a small number of completely dominant determinants. So the jump from their coefficients to the next coefficient is typically extremely large. So a system that does not have static correlation, a system that does not have static correlation is a system where there's one dominant determinant and every other determinant in that billion of them is extremely small. So if you take a simple problem like a water molecule and you do a CI calculation, you would realize that the Hartree Fock is 98 or some very large magnet fraction of the total wave function, and the rest of the small percentage of the wave function is the summation of a combinatorially large number of very tiny contributions. So static correlation is this idea that in some problems there's a few very, very important determinants. And dynamic correlation is this idea that the remaining part of the correlation comes as a summation of very tiny contributions. And the reason why this distinction is made is because if you're doing perturbation theory to calculate the contribution from the small determinants, you need to make sure that you do perturbation theory taking into account all the important determinants. If you have a problem where you have 10 important determinants, but you only refer to one as your reference, then of course the problem is not going to be very accurately solved because you are missing the contribution. There's no way that you can perturbatively calculate important coefficients. You can only do this for the weak ones. In the same way, in QMC calculations, this is going to play somewhat of a role. If you have a system where you have 10 really important determinants, but you only use one in your reference wave function, then of course your trial wave function is not very good. So you have to understand a little bit about the chemistry and the type of correlation that you have in your problem, so that you can make sure that you at the very least put all the important determinants in your wave function. Typically in molecules this is fairly easy to do. If you have a solid, then this becomes a little bit more problematic in practice. Although, to be honest, solids are not as correlated typically as molecules are. So molecular calculations from the point of view of electronic correlation are typically harder. Okay. Yes, I think I've said everything. So anyway, I don't want to get into symmetry because that's a complicated discussion, but anyway. So in addition to the antisymmetric piece, we also have the symmetric part of the wave function, which is the Jastrow. The Jastrow is the strength in many ways of the QMC method. We can directly add electronic correlation on our wave function to an arbitrarily large order, which is something that you cannot do in any other method, to be honest, at least arbitrarily. So the Jastrow is this piece of the wave function. The most important, there are many things that we need to know about the Jastrow. The most important thing that the Jastrow is doing is introducing the electron cusp condition, basically. If you don't do this, your method, your Schrödinger equation actually have divergences in it. If you think about it, when two electrons get close together, their potential energy diverges, of course. So the only way that the Schrödinger equation, that the local energy remains finite, is if the Coulomb if the kinetic energy diverges in exactly the same way to cancel the divergence of the interaction. So from that argument, if you take the Schrödinger equation for two electrons and you look at the part of the wave function where two electrons are infinitely close together, you look at the potential, you can derive what the kinetic energy has to be in order to cancel the divergence. So Kato, which it's probably done in the 50s, I don't remember exactly when, but many years ago he did this analysis and he came up with a set of conditions that the wave function needs to have when two electrons are close together in order to cancel the divergence in the Coulomb part. It's called the Kato-Cusp conditions, which means that anytime they have a wave function that depends on electron distances, the logarithmic derivative of the wave function in the limit where two electrons get close together has to have a very specific value. And this happens, there is a well-defined cusp condition for electrons of different spin, electrons of the same spin, and the electron-ion interaction. Of course, if you are right on top of an ion, there's going to be the same divergence. So the most important thing that the two-body Jastrow is doing is analytically incorporating these cusp conditions. If you don't do this, of course, you're going to have a fluctuation in your local energy, which is going to diverge in the limit when you are right on top of an atom. If you think about it, you can show that the reason why chemistry methods converge so slowly with basis set is because they're trying to reproduce a cusp condition on a two-electron wave function as a summation over single particle orbitals, because quantum chemistry wave functions are a combination of things that don't include directly the contribution from, that don't directly incorporate electron-electron distances. So you are using single particle wave functions to recover a many-body wave function. So in this figure, this beautifully shows what that means. So, and yeah, maybe it doesn't actually show, but if the figure was clear, it would. The actual shape of the wave function of the electron gas, this is an electron gas wave function calculated with plane wave, within a plane wave basis set in the limit where two electrons are getting close together. So you can see, if you could see this, there is an actual cusp here. Sorry that the figure is so bad. But it's of course, the derivative changes sign right here. And so this is showing how slowly you are converging until the actual cusp condition as the number of plane waves is increased in your basis set. So even with 15,000 basis functions, you're still very far from having the actual shape of the wave function. And in practice, you have to go infinitely far to really recover the full cusp. There's not any finite basis is never going to recover the full cusp because you're using functions that are smooth, that don't really have cusps in them. So the reason why basis set extrapolation is needed is because you need to capture this contribution to the energy, which seems irrelevant, but it's very large in magnitude because two electrons are really getting very close together. In QMC calculations, we put this behavior analytically on our wave functions, so we naturally recover cusp-related correlation directly. So to first order, incorporating this cusp is the main thing that a Jastrow is doing. Everything else is icing on the cake. Not really, but if you don't do this, your wave function is really not going to be possible, not going to be amenable for QMC calculations. Beyond that, everything else that the cusp is doing is directly adding electronic correlation for you in the wave function. And if you remember, the mentality within, I mean, probably David doesn't agree, but originally, when years ago, the idea was to use physical insight to write the best Jastrow factor that you can write without relying on optimization, right? For the newer generation, this sort of mentality in some ways has gone away. Now we think about it in a little bit of a more brute force way. So we want to have the most generic thing that we can put down, and we want to let the system optimize itself away. So we want to rely on the optimization methods and on the most generic function that we can put in there to extract the best wave function we can by relying on direct optimization. So the standard Jastrow pieces that we have in the code are electron-ion, which means it's a function of the distance between an electron and an ion, of course. The electron-electron one, which is the function of the distance between two electrons, and the electron-electron ion, or what we call the three-body Jastrow, which depends on the distance between two electrons and one ion. Of course, you can keep going. You can do 3 electrons and 1 ion, 3 electrons and 2 ions, and arbitrarily do this. In practice, it has been shown that their contribution drops fairly quickly. And on the other hand, we don't have so many hands to go and investigate some of these cases. So if you guys are interested, we would love to get a little bit of research into adding new terms, for example. But what's in the code right now it would be these 3 terms, and by far they are the most important ones. So on the right-hand side, I'm showing the energy, I believe, of a water molecule as a function of how many, the error in the energy, sorry. So this is the energy compared to the exact energy of that system as a function of what type of Jastrows we put in. So if I just put a one-body Jastrow and nothing else, and I take, of course, the Slater determinant from a Hartree-Fock calculation, this is the variational energy has an error of 0.3 or 300 millihartree. Yes, so this scale is actually wrong. This is in full. Once I include 2-body Jastrows, there is a significant reduction on my error. If I include them both, 1- and 2-body Jastrows, you can see a huge reduction on the error. So in practice, what we call best practices, or the lowest level of QMC that we ever recommend doing, is this level where you put a 1- and a 2-body Jastrow. By default, this should always be in all QMC calculations. You can also put a 3-body if you want, and that will reduce the error even further. But typically, the reduction, certainly all of my calculations are 1-, 2-, and 3-body Jastrows because the optimizer is very stable and we can just use them without thinking too much about it. But worst case scenario, always do 1 and 2. Use 3, but always use 1 and 2 at the very least. And you can see that from then to the fully projected energy, then the reduction is far smaller than the calculation without really putting the Jastrows in. So already at the variational level, your Jastrows are recovering most of the correlation energy in the calculation. DMC is just basically cleaning up any small errors that your Jastrow is not obtaining. Like I mentioned before, technically we just do, the Jastrows can be written in terms of anything. I haven't really said anything about the basis functions. So for example, in the one-body Jastrow, this is just a function of a distance. In practice, it can be a 3-dimensional function. In principle, in practice, we tend to have a function that's only of the distance, for example. So I haven't really said anything about these F functions. This is just a basis that you use to expand the actual Jastrow. So historically, Padé functions were used in the beginning. They have the right cusp conditions if you have some constraints on the relation between A and B, or you can actually, technically speaking, anyway, they are both polynomial Padé functions. But anyway, Padé-like functions, or you can, instead of doing just a single power, you can use multiple powers and still have a ratio of these Padé polynomials. So this is implemented in QMC-Pack. The more standard Jastrow in QMC-Pack, and the one we typically recommend, is the B-spline Jastrow, where instead of having a well-defined basis function For your Jastrow, we just have a piecewise cubic polynomial basis. So this becomes a completely generic basis function. You can show that effectively it would give you any type of behavior. And so the actual optimizable parameters in this case are the value of the Jastrows in some radial grid, basically. And so you optimize directly the value of the Jastrow, and then you use cubic splines to have a smooth function across the entire range of distances. So we recommend B-splines, but you can pretty much use anything you want. Everything is implemented in the code. So on the right-hand side, you can see what these Jastrow functions look like for a water molecule. These are the one-body Jastrows for the hydrogen atom, and this is the one-body Jastrow for the oxygen atom. And then you can see the electron-electron Jastrows for both up-up and down-down in red, and then the opposite spin Jastrow in blue. So of course, the cost behavior of each one of these Jastrows is different. So opposite spin never looks completely the same as same spin. They're usually close, but they're never identical. Okay. So this is a quick survey. This paper is from. So this paper up here is from early 2010, I believe. And this is a quick survey of Slater Jastrow results to give you an idea of how accurate single determinant wave functions are. This is the error in the energy from DMC calculations on what's called the G1 test set. So this is a collection of 55 molecules. And this is typically used in the quantum chemistry community to test the accuracy of a method. So if you use DFT, by the way, you're quite far away. DFT is an umbrella, of course. There are many choices of DFT. But depending on the type of DFT that you do, you can get very different mean absolute errors. So for example, if you use the simpler DFTs like PBE, and this is the S22, sorry. I don't actually have data for the average results for the G2 test set, and I apologize for that. But the average DFT error is very large in a test set like this. These are 55 molecules, so I didn't want to have all the labels in here. But these are things like oxygen dimers, water molecules, methane, ammonia, small molecules. And you're looking at the absorption energy of the atomization energies of these molecules. And this is roughly what QMC, single determinant QMC is doing. So the error is always between, on average, is close to 2 kcal per mole. I think it's 2.3 or something. And you can see, on average, it's very small. If you can systematically improve these results and make them as small as you want, if you go beyond single determinant wave functions, and we have shown this on papers in the past, you can make the method as accurate as you want by just systematically increasing the number of determinants. And then you can also do weakly bounded molecules. So this is now the S22 test set. The S22 is a test set that's meant to look at big, fairly larger molecules that are bonded by dispersion and hydrogen bonding, for example. So it's looking at a different type of interaction. And in this case, you can see that for this type of interactions, DFT is usually pretty bad. So this is on a collection of 10 molecules done, in this paper by Dubecki. And so the difference between QMC and CCSD parenthesis T, which is typically the gold standard in quantum chemistry, is better than 1/10 of a kcal in this subset of the S22 molecules that they have used. If you use the full S22 test set, all 22 molecules instead of the 10, the error is a little bit larger. It's more close to 0.3, but it's far better than what you get with with simple DFT functionals. It's much better than what you get with things like MP2, which is perturbation theory. And the only way you really get similar accuracy with DFT is by really polishing your functional. And basically, the only way you get close to QMC is by having functionals that are directly built to describe this type of interaction. So it's usually a lot of fitting and a lot of parameters that get fitted to work well in these type of systems. Okay. So within QMC, I have been talking about doing CI expansion. So the results that I just showed you are using a single Slater determinant. if you want better answers, typically single Slater determinant is quite good. In most cases, it's very close to chemical accuracy. If you nonetheless still want to improve your answer, then you have to improve your wave function ansatz somehow. So the simplest way, and this is quite trivial to do, is to do a multi-determinant wave functions, where instead of having a single product of up and down determinants, you just have a linear combination of them. And as we just described a few slides ago, in the limit where I include all combinatorially large number of them, I have the exact wave function, so there's nothing to be done. In practice, we don't need so many. A few hundred typically goes a long way in reducing errors. So typically, we actually use what's called configuration state functions, which means that you actually have an eigenstate of the spin operator. So these are spin-adapted wave functions, but in practice, it doesn't really matter. You can use CIs or CSFs. And as you can see, effectively, we have a linear combination of these spin-adapted determinants, basically. So in CSF, the Ds are determined by symmetry. So the actual number of variation of parameters if you use CSFs is much smaller than if you use CI. Now, the CI coefficients are these CIs. These are determined by symmetry. If you use something like games, you get to decide in the games calculation whether you want CSFs or CI. The converter would read either. It doesn't really care. And the QMC would work regardless of what you do. But if you can use CSFs at all, that would be better because the number of free parameters gets reduced, usually by quite a significant magnitude, actually. Then once you have these ansatz into QMC pack, we can optimize these linear coefficients using the methods that we described yesterday. Again, from the point of view of the execution, once you run the converter, the QMC knows what to optimize, so you don't have to tell it to. You can, by automatically, it would try to optimize all the free parameters in the wave function, so it would try to optimize all of these CI coefficients. But you also can you can slightly modify the input and control how many of the CI coefficients you actually optimize, or you can turn off the optimization completely if you want. The code is quite flexible in that way. But it will try to optimize everything if you don't say anything. So in practice, I'm saying here, this is quite old. I'm saying here that that it has limited applicability for extended systems. It's not quite true. You can do the same idea for bulk systems. It's just it hasn't been tested and there are no papers right now on doing this, but in practice it can be done. There's nothing really stopping you from doing this. The main limitation in extended systems is that there's no games analog for periodic systems that I can go and ask for multi-determinant expansions in a solid. If you want to do that, then you would have to use code that's written, homegrown, I would say. So I should say within 6 months or so, or depending on how much free time I have in the next semester, there will be a native way of doing this for solids inside QMC. So very, very soon, probably by the next summer school, there will be a way of doing multi-determinant expansions for solids in a completely black box way. You just say how many determinants you want and go, and the code will do this for you. But as of right now, for solids, this is not a trivial thing to do. The good thing about these multi-determinant expansions is that it allows you to include both static and dynamic correlation directly on the trial wave function. So by the time you not only systematically improve your wave function, but by the time that you use DMC on the wave function, you really get very, very accurate solutions. And if you're looking at problems like actinide chemistry, for example, or any problem that's inherently multi-reference where you will never get away from this idea of static correlation, then this is somewhat necessary because the problem is it has a lot of static correlation and you need to include that static correlation on the wave function. Any questions? Any comments? Any concerns? Philosophical discussion? No? Okay. Please stop and I can talk about anything. Just let me know. Yeah.
What is the plane wave counterpart of the multi-determinant feature? I mean, it's high frequency.
What is the plane wave counterpart of what?
I mean, in a wave function based theory, you use multi-determinant to recover the static correlation, right? But if in a solid and you use plane waves, so how do you recover the static correlation?
So in a plane wave calculation, we'd still use a single particle orbital, which is not a single plane wave. It's still a linear combination of all the plane waves that you include in the basis set.
Oh, okay.
So, and then on those single particle orbitals, we do determinant calculations, and you can include different type of single particle orbitals. So you can, typically you do your Hartree-Fock or your DFT determinant, which is all the lowest bands, but you can include excited bands. You can do a determinant where you remove one of the occupied bands and you occupy a band that's in the conduction band, for example.
I see.
So in the limit where you include enough of these determinants, then if there is static correlation in the solid, then you can recover it back. The problem is that, of course, a solid is infinite. So the amount of configurations that you need is typically, in principle, infinite too. So the benefit of QMC is that we don't recover correlation with the wave function. We reduce the fixed node error. So what you can think about it from the point of view of improving the variation of freedom of your wave function by including more determinants. This is not the way chemists think about it, where the determinants are actually capturing correlation. We just think about it as variation of freedom. So if you include enough of these determinants, the wave function would reconfigure itself by optimization and give you the best ground state that you could do. So again, the only limitation in solids really is just available mean field software, because this is not an idea that makes a lot. To do a full CI expansion in a solid is not something that makes complete sense. This hasn't really caught on. But from the QMC community, it's not really about doing a full CI expansion. Again, it's about variation of freedom. So for us, this is valuable in practice. And so this is being worked on. This should be available fairly soon. It's just not available right now. But in my developer's version, it is so. So these are a lot of equations. Anyway, in case this is not everybody, of course, this will not be relevant for everybody. If you want to become more of a user, then you don't need to know these things. But if you want to know a little bit of what goes on inside the engine, then this is what's actually implemented in the code. Again, in the multi-determinant case, the wave function is written as a Jastrow times this multi-determinant expansion. I describe here CSF expansion. So in practice, it just means that you have two sets of coefficients and they multiply each other. And you just vary the C's and you keep the D's fixed. Of course, you have to do the gradient and the Laplacian of these determinants. So you can show with a little bit of linear algebra that this is the expression for the gradient of the determinantal part of the wave function, sorry, of this part only. Yeah. So we split it between Jastrow and an antisymmetric piece. So the gradient of the antisymmetric piece is, again, a linear combination of the gradients of the individual Laplacians and then weighted by their products. And the Laplacian is this similar expression where you have now independent terms and then you have this mixed term that couples the two, because, of course, you can take mixed derivatives and couple the two. For VMC optimization, of course, you also need to know the gradient with respect to the parameters. But because the parameter is just a linear parameter, it just amounts to all the terms that are coupled to a particular k in this expansion. So it's fairly straightforward. So in practice, when we do the calculations, we have to evaluate a long list of these determinants. And then with the list of determinants, we just assemble these different sums. The most expensive part, of course, these sums are linear in the number of terms. The evaluation of these determinants is cubic. So the most expensive piece is actually just evaluating the very long list of determinants, very long, a few hundreds. So if you do this naively, then if you have n determinants in your expansion, then the cost to evaluate the wave function is just n times a single determinant wave function, which would mean you scale linearly with the number of determinants. We recently, I mean, not so recently, in 2011, we came up with a faster algorithm to do this. In practice, there is no reason to pay the full cost of evaluation of a new determinant if you just evaluated a determinant that that's very similar to it. So because we work in the particle Hall basis, we typically do 1, 2, maybe 3 excitations away from a well-defined reference. So if you think about it, if you have 100 electrons and you're just changing 3 orbitals, there's no reason to evaluate the full determinant and the full matrix inverse for something that has only 3 columns that are different. So there are well-defined techniques in linear algebra. It's called the Woodbury formula or the Sherman-Morrison formula or the generalized matrix determinant lemma that allows you to evaluate determinants and inverses between matrices that are only changing by a small number of columns. So the fast algorithm is basically, there are different ways of speeding up multi-determinant calculations, I should say. There are probably 3 that are used in different codes. We believe that our way is the best, and we would compete against anybody. If you have your method, come and talk to us. But in practice, it actually leads to a huge improvement in multi-determinant expansions. And you can basically, you can go to this paper if you want to know all the details. But it relies on pre-computing. Basically, if you can pre-compute data, what we call the index table, which is basically matrix elements between excited and occupied orbitals. And you can show that this table is all you need to recompute matrix elements, the ratio between Slater determinants, between arbitrary Slater determinants. So if I have a determinant, if I have already evaluated a determinant and an inverse, I can evaluate the determinant and the inverse of a matrix that has changed by m columns by the determinant of an m by m matrix. So if I just change 2 columns, I just need a 2 by 2 determinant, which is much smaller than an n by n determinant. So that means I can do very, very large number of electrons and still keep the cost of the multi-determinant expansion to how many excitations I am putting in the determinant and not to the number of electrons that I began with. And so basically this, and generating this table is very quick also. So in practice, when you test what type of speed up do you get by doing this table method compared to the more naive method where you just reevaluate determinants from scratch, you get speedups typically on the order of 20 to 30, even by this, using multi-determinant expansions that are way on the thousands. So in practice, we're able to do several thousand determinants on a multi-determinant wave function, and the extra cost is it's way less than 2 orders of magnitude for including, 5,000 determinants or so. So this is a very nice thing that makes these multi-determinant expansions just routinely available for QMC calculations. In the past, multi-determinants were not really that used because the cost was fairly high. If you want to put 1,000 determinants, you don't want a DMC calculation that's 1,000 times faster. But you can put 1,000 at a cost of maybe 20 or 30 now. So some applications of multi-Slater determinant wave functions. For example, I show a figure that's somewhat similar to this one, but if you take the water molecule, for example, and you plot the energy that you get, so you get variational energy on the top and DMC energy in the bottom. This is the energy that you're getting as a function of it's really, technically speaking, it's the square sum of the configurations in the initial multi-determinant expansion. And in the top, you can see this also as the number of terms that you're putting in the multi-determinant expansion. And you can see that both variational and projected results converge systematically decrease as you keep increasing Slater determinants. And for the DMC results, it systematically approaches the exact answer, which is on green for the water molecule. So basically, by including a few hundred determinants, like I mentioned, you can get answers that are very, very close, within a millihartry or so of the exact answer. You can do the same, for example, in more complicated problems. This is a case of a triradical. And we're looking, and I apologize again because the figure doesn't look very clearly. It's not very clear, but you can look at the relative energy between 2 different isomerizations of the triradical. And typically, this is a very delicate calculation which requires high-level quantum chemistry to do. In QMC, if you don't use a multi-determinant wave function, this is on this axis now, this is proportional to the number of determinants. You typically get a pretty bad answer if you do this with a single determinant. But by including a handful of determinants, and at this point we probably have a dozen or so, you get a very significant reduction in the error. And once you start increasing, in this case, we're interested at the energy difference, of course. So at some point, we just converge, and any further increase in the number of determinants just give you a reduction in the energy, but which is consistent between the two states. So the relative energy is converged with a dozen or so determinants. You can also look at this as a systematic way to improve arbitrary calculations, like I did here. So this is also a paper that we wrote some years ago, where we look now at the same test set that I mentioned a few slides ago. It's really the G1 test set, 55 molecules. So in that case, if you do single determinant, we were having errors that were on the order of 2.5 to 3 kcals per mole. Couple cluster theory, in the limit where you extrapolate to the infinite basis set, which is a careful and a delicate thing to do, but if you know how to do this, then you effectively get chemical accuracy, much better than chemical accuracy. So this is the golden standard. If you want to, we can use DMC calculations and increase the number of determinants systematically, and we can show that in the same way that you get better and better answers by increasing the basis set in CCSD, we get better and better answers by having a more determinants in the trial wave function. So this gives us a systematic way of improving our results to arbitrary accuracy. There's just one number that I'm changing between different calculations, and everything else is the same. Of course, if you do CCSD, this is just to show, this is CCSD using the latest of the latest in quantum chemistry. If you're a chemist, you understand what F12 is. If not, this is a very clever way of capturing the cusp, the energy related to the cusp, the electronics cusp in CCSD. This only really appeared a few years ago. Probably now a decade, to be honest. But it's not one of these methods that have existed forever. This is very, very new. And so this is the only way that you can kind of compete with QMC. If you don't do something as careful as that, you have to rely completely on basis set extrapolations. On this side, I have the same CCSD parenthesis T, but now using triple zeta, quadruple zeta, and quintuple zeta basis sets. So you have to go way beyond quintuple zeta and extrapolate to the infinite basis set limit to really be able to get results that are comparable to QMC. And if you do DFT, for example, or MP2, then the results are much worse, and there's no real systematic way of improving them. Whatever you get with PB, then that's what you're going to get. There's nothing to do. Anyway, so this is just to show that there is a clear systematic way of getting better answers for molecules and in the future for solids too. When you start doing multi-determinant calculations, of course, there are some choices to make. Typically, this is fairly black box to use, but the more you know about the problem, the faster the convergence and the better answers you can get. The actual multi-determinant expansion depends on two things. Which configurations do I put in my calculation, and which set of orbitals do I use to do the expansion on? If you think about it, I can use any DFT, for example, to generate a set of orbitals and then do multi-determinants on those set of orbitals. I can use Hartree-Fock, I can use CASA-CF. There are different choices of methods. And one choice is how to generate the orbital set where the configurations are going to be chosen. And by configurations, I mean different excitations away from my Hartree-Fock. And then a somewhat independent choice is how I choose from these billion configurations, the 100 configurations that I want. There's still some things to improve in this area, to be completely honest, and I encourage you guys to think about this. You probably can come up with a breakthrough that makes this much better than it is right now. So right now, we somewhat rely on knowing a little bit on the system and on having some chemistry method that does the pre-screening for us. So when you do the games calculation, you typically have to do a sort of a CI type of calculation with games. And that CI would give you an ordering of determinants according to that level of theory. So we typically rely on that to choose the most important determinants according to CISD or CISD TQ or your favorite truncated CI approach. So we rely on having a direct diagonalization to pre-screen determinants for us. Then we choose the best determinants, and we use that in the QMC calculation. So on this figure, I'm trying to show the difference between choosing different type of the DMC energy as a function of the, again, we use this measure because it gives you a nice way to extrapolate, which is the square sum of the CI coefficients, but you should think about this as a measure of the number of determinants, where in the limit of 1, we have put all of the determinants in the system, and then we get there with some monotonic way. And so if I do so if I do CAS CI, so that is, I take a small number of orbitals and I do a full CI calculation on this small number of orbitals, and I choose the best determinants according to this full CI calculation. Then I choose determinants according to this. This is where the same water calculation that I showed here. So the scale is not the same, but it's the same system because I'm using a pseudopotential in this case. This is how the DMC energy converges to the limit of including all of the determinants that the CAS CI believes are important. If I now do CISD, for example, singles and doubles outside my Hartree-Fock, then I get a much better energy. So this means that states that are fairly high in energy, these are coming from basis functions that are, from single particle orbitals that are not included in my CAS CI, are actually contributing significantly to my wave function. And if I do second order CI, which is a combination of these two, it's effectively a full CI on a limited set of states, and then I consider singles and doubles outside this complete active space, then you can see that effectively this wave function combines contribution from this and from this. Then you really get I think the exact answer is somewhere down here, somewhere 72.5, I believe. So you get something that nicely converges onto the exact answer. So we have different choices, and so which particular choice you use depends on what you have available, whether if you can afford second order CI or if you can only afford CISD, for example. And it also depends on the set of orbitals that you use. If you do this on a Hartree-Fock set of orbitals, you're probably going to get a slightly worse result than if you use CAS-CF orbitals, for example. There's a recent paper that we wrote on analyzing basically and discussing a little bit about the interplay between these two choices, so you can go and read it. If not, you can come to me and we can talk about these things. Sorry. I wonder if no, okay, we can keep going. So there are alternative ways to improve the trial wave function. I have discussed already the more CI way. This is including more and more determinants in your expansion. There is an alternative way which came out of work done by David Seberly, who I don't think is here, but it's called the backflow transformation. He might have hinted at this in his slides. I don't recall. But basically, this is the idea of thinking about quasi-particles in a sense. So this is coming more from correlated problems in physics, liquid helium in particular. So it's the idea that at the end of the day, we want to use a single determinant calculation, or it can be a multi-determinant, but to understand what's going on, we don't need more than a single determinant. We want to use the same expression that we had before, a determinant multiplied by a Jastrow. I'm omitting the Jastrow. This is just the antisymmetric part. But now I want to do the determinant not on the original set of orbitals. Okay, sorry. Yes, so I have a set of orbitals that I've always had before. So this comes from some mean field calculation. But instead of evaluating the orbitals on the positions of the electrons, which would be the R's, I want to evaluate the orbitals on quasi-particle coordinates. So I take my initial coordinates of the electrons and I do a quasi-particle transformation. I go from R to X, where X now knows about electron distances. So I do this mapping from electron to quasi-particles, and then I evaluate my orbitals in the quasi-particle coordinates. This, in practice, allows me to modify the nodes of my wave function. And it also allows me to incorporate information about electron distances in my coordinates. So this is, once you have done this transformation, there's a little bit of algebra that you need to do in order to go from now the determinant of the orbitals evaluated at the quasi-particles to, evaluated at the particles to the determinant evaluated at the quasi-particles now. Now we need to know also how the gradient of the orbitals change, what the gradient of the orbital with respect to the quasi-particle coordinate is, and what the Laplacian of the orbital with respect to the quasi-particle coordinates are. These now become matrices, of course. And then there's a little bit of a change in terms of the gradient and the Laplacian of this new of the logarithmic derivative of the determinant. And there's even a little bit more change when you take into account changes with respect to the variation of parameters, which would live inside this radio function. But this is all implemented in QMCPAC, and it works very well. And it gives you an alternative way of improving trial wave functions. This is a much better way at improving. If you don't have static correlation, this works extremely well. If you have a lot of strong static correlation, then you probably want to combine a multi-Slater determinant that contains all the important determinants, like I mentioned, and then put backflow transformation on top of that. And then that will give you a very, very, very accurate wave function to use. So the reduction in the energy given by backflow transformations is usually very large because it allows the nodes to relax in a way that improves the energy significantly. I believe David mentioned this. This is all based on Feynman-Kack's formulas. If you have questions about this, we can talk about it. This is something that not everybody uses, but it's well implemented in the code and it works very well. So if you have any questions, let me know and we can talk about it. There's some very, very good papers describing the effects of these transformations, which you can go and look at. This Kwon's paper is on the electron gas. On the electron gas, backflow correlations are extremely important. And then the Casino group also has a fairly long paper on how to implement this and the effects of these things on molecules also. There's also a very good paper by Lubo-Schmitas, which if you're interested, you can ask me. So now, in terms of application of backflow and the combination of backflow with multi-determinant wave functions, this is a paper that we wrote recently looking at, let me see what we're looking at. Oh, so this is the energy of single atoms on the first row, and this is showing how if you go from VMC and DMC calculations, this is the typical error that you get, the fraction of the correlation energy that you gain. So of course you want 100% of the correlation energy, and this is if you include backflow transformations. Yeah, so Seth is including a short multi-determinant expansion with backflow. You can see how effectively, by the time that you do DMC on this type of wave function, you recover effectively 100% of the correlation energy for the atoms. And I should say that he's including only 50 determinants in this calculation. So it's a very, very short expansion. By the time that you put backflow on top, then for small molecules, you're effectively very, very close to exact. This is from Kwon's paper. This is from the second one of Kwon's papers with David separately. And this is showing how for the electron gas, the energy gets systematically reduced. If you go from a Slater Jastrow wave function, this is including only two-body Jastrow. When you include three-body Jastrow, you get, this is now the energy, as a function of the variance. So if we remember from yesterday, in the limit where the variance goes to 0, the energy becomes exact. And so by the time that you include backflow, including backflow with the two-body Jastrow is much better than including a three-body Jastrow. And by the time that you do fixed node, which is a DMC calculation, you're very close to the exact answer. So these 3 points are variational calculations. There is no projection at all. And by incorporating backflow on top of the Slater Jastrow wave function, you recover most of the correlation energy that the Slater Jastrow is missing. So from there to a full projected energy is a very small amount of energy that you're missing. And this is another paper showing basically the exact thing. This is a paper by Seth showing how you get better than 99% of the correlation energy by the time that you include a handful of determinants on top of your backflow calculation. So to reiterate this, if you combine both, you only need a very small number of configuration state functions to match the accuracy of a much, much larger CSF expansion. So the combination of the two is actually quite powerful, especially for small molecules. So as I was saying a few minutes ago, backflow transformations are one of the ways of improving your trial wave function. We already discussed multi-determinant wave functions. We already discussed backflow transformations. By the way, if you realize, I didn't spend much time talking about Jastrows because, in a sense, optimizing the Jastrow is a fairly simple thing. The optimizers work very well, and we can use very robust Jastrow. So from the point of view of the Jastrow, there is not much to think about. It's just, do you want to put 3-body or do you want to even go beyond that? But once you make that decision, then the code takes care of everything, and it's fairly straightforward. The entire improvement of the trial wave function, or the part that's delicate, is the improvement of the antisymmetric part, because this is the part that controls the fixed node error. If you remember from David's lecture, the entire fixed node error is related to how different the nodal surface of the trial wave function is from the exact nodal surface. So if you do a DMC calculation with a poor Jastrow, as long as you keep the nodes in the same place, DMC is going to recover the error that you have from the point of view of the Jastrow correlation. Having much better Jastrows, of course, are going to lead to much more efficiency on the DMC simulation. You can use larger time steps and smaller populations and so forth. So you really want to have the best Jastrow possible, but the Jastrow doesn't reduce the fixed node error. The only thing that reduces the fixed node error, which is the ultimate approximation of the method, is the nodal surface of the trial wave function, which is completely defined by the antisymmetric piece, which is why we spend so much time talking about the different alternatives that you have to add flexibility to your trial wave function, to your trial nodal surface, and which you can then optimize away and get better wave functions this way. So like I mentioned, the multi-determinant expansion is the simplest one. And for molecules, in particular, this is probably the only thing you have to consider, unless you're doing something that's very, very complicated. So typically, if you do CI calculations with games, for example, then you can just keep increasing the determinant expansion until you get good answers. If you want to consider backflow transformations, these are not as universally used as multi-determinant expansions, but they are a very efficient way of capturing dynamic correlation. There are other alternatives that have been tested in the community. Not all of them are implemented in the code right now. We're working on that, and they should be available in future distributions. And these are all related to, for example, pairing wave functions. So this is the idea of, instead of using a Slater determinant as an antisymmetric piece to the wave function, a Slater determinant is an uncorrelated wave function. So it's a product of single particle wave functions, basically. It doesn't have any correlation between electrons. You can incorporate pair correlations and higher order correlations into your antisymmetric trial wave function if you consider now an antisymmetric function of functions that incorporate more than one electron coordinate at a time. The simplest example would be what's called a pairing wave function, or a Gemino wave function. A Gemino wave function is strictly speaking, is the natural orbital basis of the two-particle reduced density matrix. But you can think about it as just a two-electron wave function. And so we build a many electron wave function as an antisymmetric product of two electron wave functions. And the good thing about this is that most of the electronic correlation is captured at the two electron level. So if you can use this wave function to begin with, now you have a wave function that's much more flexible and much more accurate to begin with. The negative side is that it's much, much harder to do pairing wave functions at the mean field level. So from the QMC point of view, it's not much more expensive and it's not much harder to use them, but it's much harder to get mean field solutions that we can use as input to the QMC calculations, which is why typically these wave functions are not universally used. This is changing, by the way. There are some excellent step forwards being developed that will, within some amount of time, would actually make this type of wave functions standard or universally applicable in QMC. You should look at the work of Eric Nuskamant, for example. He's doing excellent work on this area. There are different flavors of pairing wave functions. That's what's called resonating valence bond. So if you know superconductivity, this is one of the propositions that would explain high temperature superconductivity, although, of course, it hasn't really been completely successful. But this is Anderson's RBB. This goes back in chemistry to the 50s, the work of Pauling and describing states in benzene rings, for example. And so it's basically the simplest way of writing a wave function that incorporates geminal. So if you think about it, a determinant is an antisymmetric product of functions that depend only on one coordinate. A resonating Balanced bonds or an AGP wave function, there are different names for this because this has been reinvented over and over and over. It's an antisymmetric product of a function of 2 electrons at a time. So in the RBB case specifically, you get a geminal of up and down electrons. But of course, you can generalize this in the case of Pfaffians to an antisymmetric product of up and down. The up and downs go here, the up go here, and you can have even singlet paired electrons. This now, in order to have an antisymmetric structure for the more generalized case, you can show that this is not a determinant anymore. So this antisymmetrization leads to a determinant of these geminal pairs. In the case of the Pfaffians, this is now a Pfaffian of this pairing matrix, which you can show that it's related to, it reduces to determinants if you only take into account the opposite spin correlation. There's a very nice paper by Lubos Mitas and Mikhail Bagdish from 2008. They were the ones who pioneered the introduction of these wave functions in QMC. And so this wave function has some issues. If you want to go at depth about what are the limitations of this type of wave functions, you should read the work of Eric Nusskamman. But if you do use this naively, then this is not a very good wave function once you start doing bond breaking, for example. So if you're away from equilibrium, there's some issues with this wave function, which can be fixed by the introduction of a Jastrow, actually. So something that chemists don't really think about too much about these wave functions, because without a Jastrow, they're not very good. But if you're able to put a Jastrow in many body space, then you can remedy some of the deficiencies of this wave function. So if you're interested, I strongly recommend you read the work of Eric Nusskamman from the last 2 or 3 years. So this is currently, we're trying to develop ways to incorporate these wave functions in real space, QMC. They are very easy to incorporate in orbital space, but in real space, there's some tricks that have to be played. So in some amount of time, this would be available, and I actually believe that this would be a very, very important jump in terms of the type of wave functions that we can use, so we can finally go beyond Slater determinants. The cost is about a factor of 2 compared to the Slater determinants, so it's really not much more. But the flexibility is incredibly enhanced compared to Slater determinants. You can show that you can decompose this wave function into a multi-determinant expansion, and it has contributions pretty much from arbitrary configurations, as long as you include the corresponding orbitals in the definition of the geminals. And then finally, there is the work of mostly Claudia Filippi and her group. There have been several iterations of this work, but she's been doing work on generalized balanced bond theory. So the idea on her, so her ultimate goal is to have a size-consistent multi-determinant expansion with a control recipe, basically. So if you do multi-determinant expansions, they are combinatorial in cost, of course, and they are exponentially increasing cost with system size. So she wants to come up with recipes and well-defined procedures that allows us to build multi-determinant wave functions whose quality does not change with system size. Of course, the number of terms is going to grow with some polynomial dependence of the system size, but the whole point is to keep the cost polynomial and to keep the accuracy homogeneous with system size, which would allow us to do QMC calculations without the QMC, without the exponential explosion. So if you're interested, there are 3 or 4 papers by her group, Claudia Filippi from somewhere in Netherlands, Leiden in Netherlands, yeah. So this is excellent work, and I strongly recommend anybody interested in looking at this. And so, but the idea is basically to use linear scaling and local, to decompose the orbitals and localize them in such a way that you only correlate with orbitals that are in the neighborhood of your orbitals. So you would consider, for example, bond regions in a molecule, and you do controlled expansions using orbitals that only overlap or that are very close to the orbitals involved in the bonding, basically. And she has shown that you can do this with well-controlled polynomial growth, and the more the more involved the amount of, the more configurations she includes, the more these wave functions get systematically better. This hasn't been incorporated. This right now only works for solid state for molecular calculations, but there are some people working on the extension of this idea to solid state, and that would be quite an impactful thing. Not right now in QMC-Pack, but effectively, so the ability to use the wave function exists in QMC-Pack right now. The ability to generate this selection of configurations is not. So this is something that we're talking to Claudia, and at some point it's going to be incorporated. But if she gives you the expansion, you can use it in QMC-Pack, So we already discussed all of this. I just want to discuss it again and to make sure people don't have questions, because this is going to be basically the lab that you're going to be doing later today involves using more complicated quantum chemistry methods to generate input trial wave functions for QMC that then you optimize at the QMC level, and you will see how the energy of a water molecule gets improved and becomes very close to the exact result. So you'll get to systematically improve and use all the functionality within QMC-Pack to do this. So to make sure that the lab is going to have a lot of nomenclature, so to make sure everybody understands, I want to go through this again. And please, if you have questions, this is the time to ask, because probably in the labs it's going to be a little bit harder to ask the questions. So it all, if you remember, it all goes back to the idea of configuration interaction. So configuration interaction, again, is the idea of diagonalizing a Hamiltonian within some basis of determinants. So how do you generate the determinants? It's what gives the method the name. So if you want to do what's called full CI, then you generate all determinants in the Hilbert space. So that means some reference determinant and all possible excitations of that determinant away from the reference, single, double, triple, all the way to all electrons being excited, and all excitations in all possible empty states, basically. So the scaling of this thing is going to be, of course, combinatorial. It's all the possible ways of distributing n electrons in m orbitals, which, if you take into account spin, is actually the square of this now. It's very close to the square of this number. So this is full CI, which, of course, nobody really ever does. You have to truncate full CI. So instead of doing all possible excitations, and I have a diagram, which I haven't used, and I should be using, and I'm sorry. So let me start with the diagram and then go back a little bit. So let's assume that we have done some Hartree-Fock calculation, for example. We have some set of single particle orbitals. And so a Hartree-Fock calculation, a Hartree-Fock solution would be, let's assume that we have 6 electrons, or that these are the occupied orbitals in the Hartree-Fock state. Of course, they're ordered by eigenvalue energy. So you have the lower energy states in the bottom and the higher energy states up here. So the Hartree-Fock solution is nothing else than the determinant that occupies all the lower energy states, as many as you need to put all the electrons in your system. Let's assume that the system is closed shell for simplicity. So closed shell means you have 2 electrons, one up, one down in each one of these orbitals. And your Hartree-Fock solution is a product of the up determinant and the down determinant. So in all of these CI methods, we typically split up the orbital space into 4 spaces. So we typically have frozen orbitals. These are core electrons that are deep in the energy scale. They don't really contribute to chemistry. We don't want to take them into account into the correlation calculation. So they're just frozen. They are never, basically frozen means that they never get excited in the correlated calculation. You can include them in the QMC, but they would not be part of the excitation structure of the multi-determinant calculation. Then you have occupied orbitals, which are going to be from the Hartree-Fock state, the ones that are not frozen. And then you're going to have a set of active orbitals. Active orbitals are the orbitals that are going to be involved in a CI solution of a restricted space. So typically in quantum chemistry, you include low energy states that are, you typically complete the shell that you're in. But for example, if you're doing first row atoms, you typically go all the way to 8 electrons, 8 orbitals. But the actual choice of the active space is typically very dependent on the chemistry of the problem. So you want to put in the active space any orbital that's involved in the bonding. So any orbital that gets modified during bond breaking, for example, you certainly want to put it in there. From the point of view of the QMC, we can just always take the bottom energy and some number of states above the LUMO and then use that as the active space. If you have chemical intuition and you know exactly what orbitals to choose, then this would, of course, make things a lot easier. But if you don't, then just choose as many states as you're interested in taking. So let's assume that we have made that selection and we know exactly how many active space orbitals we want. Whatever is left is typically called the virtual space. So let's go through the hierarchy of CI methods and see what each of these methods is. So full CI, again, is all possible excitations of these electrons in all possible orbitals, and then you diagonalize all of that mess of determinants that gets created. If you do truncated CI, then we do a certain number of excitations either in the active or in the virtual space. You generate all of these determinants, and then you diagonalize. So for example, CISD would be take any two occupied orbitals, remove the electrons from them, and place them in any two orbitals up here. The number of determinants in CISD would be the square of the number of unoccupied orbitals times the square of the number of occupied orbitals. With spin would be the square of that, but effectively, if we forget for now, the spin. So CAS, and then the next level would be CAS-CI. So CAS-CI, if we remember, is the idea of let's forget about these virtuals up here. If the correlation is really stronger among the active orbitals, then CAS-CI would be let's do a full CI, but only in these orbitals right here. So all possible excitations away from my occupied states, but only on a very small subset of orbitals. If you do CAS-SCF, it's exactly the same ansat, but now you include orbital rotations between virtual and occupied in such a way that you get the best, you basically do orbital optimization within an ansat that includes all determinants in this space. So typically, if you have a molecule that has strong correlation, you typically have to do CAS-SCF because the Hartree-Fock orbitals are rarely good. So at the very least, you get a set of orbitals that are much better because you include the correlation coming from the low-lying states, which is typically strong. Okay. So multi-configuration self-consistent field is what I just described. It's this idea that you combine a CI calculation with an orbital rotation that allows you to get optimal orbitals for whatever ansats you have. So in other words, you're pulling correlation in many ways from the virtuals all the way down to the active space and optimizing the orbitals. So you can show that this gives you the optimal or the best possible energy for the selection of determinants that you have made, basically. And finally, there is a combination of the two ideas. You can do what's called second-order CI or multi-reference CI, and we will be doing this you will be doing this on the tutorials, where now what you do is you do the same idea as before. Now you do a CAS-CI calculation where you include all the determinants that you have on this space. And then you, on top of that, for each determinant that you just generated, you also consider single and double excitations onto this space up here. You can show that second-order CI for most calculations is an extremely accurate level of theory. It's also quite expensive to do in practice, so it's not that popular, to be honest. But the hardest problems are typically in chemistry treated at the second-order CI level. The number of determinants that you generate is extremely large. So you typically can only do small systems with this. With QMC, we only need a handful of them. So we only really use the second-order CI approach in QMC to be able to find the important determinants and then use them in QMC. So you go from billions to hundreds, like I mentioned. But you get the 100 that you use, you end up finding determinants that you would otherwise not find if you don't do this type of approach. Okay, so this is just a quick refresher. You would be doing truncated CI, CAS-CI, and second-order CI, I believe, on this second part of the tutorial in the afternoon. And you will be using that to generate wave functions for water calculations. for your own research projects, you can effectively follow exactly the same work, just substitute the water with whatever it is you're interested in. And then, of course, if you do a molecule that's too big, then you might not be able to afford secondary CI, or you might have to play a little bit with how many orbitals you put in the calculation. But the steps, once you make those decisions, are effectively the same. So this would show you the steps and the workflow to be able to do these calculations on your own. So I want to go very quickly through some applications that have used QMC to kind of give you a flavor of the type of research projects that people are doing and the type of calculations that people are doing. Not all of them are with QMC pack, so at this point it's just to give you more of a flavor about QMC for molecules. Some of them are done with QMC pack, but so for example, I have been involved in considerable amount of work in water, and the idea here is this is really bulk water, but it's still basically the chemical relevance is what gives us the motivation to do this work. And this calculation shows we take a big set of configurations from MD calculations of water, and we use QMC. We generate hundreds of these configurations, and we do very, very accurate QMC calculations. I don't know if you're familiar with this, but water is it's close to being probably the most studied system in chemistry. It has relevance in biochemistry, geophysics, pretty much anywhere that you look, water is a very important topic. And so from the point of view of computer simulations, the description of the properties in the liquid are very challenging. So to get, water is considered an anomalous liquid. It has a lot of properties that really most liquids do not show. For example, if you cool the liquid, the density has a maximum, and the compressibility has a minimum. There are a handful of properties that are really strange in water. So getting those properties described within first principles is a very, very, very important challenge. It's only recently, in the last year or so, that actually tools have been developed that seem to be getting close to a solution. But as of right now, it's still very much a research topic. There are probably dozens of papers on liquid water every year. And a lot of computing time gets spent on water, actually. So if you think, I can probably right now go and print 100 papers on the study of liquid water using every functional in existence and every approach in existence. So from the point of view of DFT, which is the workhorse in the first principles community, DFT really has a lot of trouble describing water. But nonetheless, people are really, really trying to get a functional that will describe water accurately. So what I'm trying to do here in this article is trying to use QMC to try to understand why DFT is so, what is so challenging about water for DFT. And so, for example, I have some configurations that I drew from a set of simulations where the water molecules are frozen. And so you get frozen monomers that are moving around in space, but you don't let the water molecule vibrate. And there are some configurations drawn from path integral simulations using density functional theory. So now, not only is the water flexible, but also you get 0-point energy, which allows for much larger vibrations that you would otherwise have gotten. And you can see that, and then what I'm showing here is the error in the energy compared to QMC, which for water is a very, very accurate benchmark. I mean, if we could afford QMC, dynamical calculations of QMC on big water cells, effectively we would be able to obtain a very accurate description of water. So there are two things that you see. On the one hand, you see that if I don't let molecular vibrations occur, and if I treat the water classically, there are no molecular deformations, and the fluctuations are much smaller. So the energy scale of the errors are much smaller than when I do full quantum simulations with flexible molecules. And then the other thing that you would show is that, so all of these functionals up here they're not hybrid functionals. I'm only doing 3 hybrid functionals. Sorry, you cannot really see this, but you can probably see it better in the computer. I have B3 leap, I have PB0, and I have B3 leap with dispersion correction. And you can see that there is about a factor of 2 difference in the accuracy between functionals and non-functionals, and hybrids and non-hybrids. So if you want to get an accurate description of water, first of all, you need to have, there don't seem to be any non-hybrid functionals or GGA functionals that would give you anywhere near the quality of a hybrid functional. And you need to, if you don't do this, it doesn't really matter which functional you use. You're sort of wrong almost equally in all places, in all cases. There's a follow-up to this work that we should be publishing soon, where we try to add corrections to the FT based on an analysis done with the bulk calculations in QMC, and you can show that you systematically can improve the DFT, but you have to do a lot of work to get there. So in other words, DFT is just not a very good level of theory if you want to do weakly bound systems like water. This is work, so our work was inspired in many ways by the work done by Mike Gillan, where he now uses QMC also to look at water, but he's now looking at the errors in DFT and in approximate theories as for clusters, and as the cluster size gets enlarged, he compares to really accurate calculations with couple cluster, and he shows that the difference between QMC and couple cluster is very, very, very tiny. It's much smaller than any error that we need to take into account. So this gives us the confidence that bulk calculations are really predictive in our case. Miguel A. and his student, they have been looking at proton transfer in water clusters recently. So in this case, they're showing H5O2, I believe, where they are looking at the transfer of a proton between two water molecules. And so they can show how they can very accurately describe this process using QMC. These calculations up here are for pure water. So if you consider now proton transfer and proton exchange, then you're really asking for a lot out of density functional theory. So if you want to get a good description of these things, you really have to either just abandon density functional theory and go to something like QMC, or really work really hard at the DFT to be able to tune it basically to give you reasonable answers. And also, the same group that did these calculations, they show how if you're looking now at the cohesive energy of ice, again, DFT has a lot of trouble. In this case, the red dots are experiment and the blue dots are QMC calculations, and these are three different flavors of DFT calculations, all with either hybrids or van der Waals corrected density functional theory, and you can show that neither really is good enough at describing the cohesive energy of the liquid. So that means that if you are doing calculations of ice at high pressure, for example, your phase lines are going to be all over the place depending on which functional you use, because the relative energy between these structures is just completely wrong at the mean field level. And this is well known, because if you do DFT, nothing comes out what it should be, basically, about that. So excited states is another area where considerable work has been done. Again, this is mostly done in Europe. There's a lot of work by Claudia Filippi, by Sandro Solela, by, forgetting his name, and he's in Rome. Anyway, he's also in L'Aquila. Guidoni, yeah, sorry. So Leonardo Guidoni has also done a lot of work. So in this case, there are not only the calculation of excited states, but for example, Claudia has been able to come up with ways to optimize geometries for an excited state calculation. So it's identical to the linear method, but instead of using the linear method to give you an optimization of the ground state, you can actually use solutions for the excited states in the linear method, and that will allow you to walk on the excited state surface. So she has been very successful at looking at optimization of geometries and calculation of properties for excited states. If you're interested and if this is close to your field, then you should really take a look at Filippi's work. She has been really pioneering this type of calculations. And there's also things like bond breaking and rotation or torsion of molecular calculations, where excitation is really important. So I guess I don't really want to go into a lot of detail about what these calculations are. They're typically involved photoactive biomolecules, but the accurate accounting of correlation on excited states is completely critical. Mean field methods almost always give you really bad answers. So QMC gives you an alternative, which is, again, it scales very well and it's very accurate in practice. If you have any questions, we can talk about it in some detail later. This is now, the work of Filippi, and this is the work of Guidoni and Sandro Sorella and their students, of course. So in this case, they're looking at barrier heights. On this case, they look at chemical reactions, and they want to look not only at the identification of the path, but also at the identification of the barrier and the relative energy between products and reactants. And in practice, they have shown that QMC is very accurate. Again, now mean field methods are almost always terrible at looking at transition states. So in this case, you're really comparing with high-level quantum chemistry calculations, and even then, these methods are not as easy to use and are not easy to control once you're looking at excited state properties. But QMC, as Claudia has shown, that QMC again is a very powerful tool to look at these problems. So again, look at her work if you're interested in properties related to excited states and transition states. So the other thing that has been, the Italian group has been particularly successful at is at extending calculations for molecular properties beyond ground state and excited states. So for example, this is a calculation of molecular polarizabilities recently published on ethene, on ethene by Leonardo and by Sandro Sorella. And they have also been looking at, properties of die radicals and looking at, the deformation energies and at the proper description of different deformations, which are particularly hard because they have very, very strong static correlations. So if you want to do even quantum chemistry methods, like couple cluster will probably fail because you have to have multi-reference involved in the calculation. So QMC gives you a very straightforward and a very natural way to describe this delicate correlation that comes into this type of calculations. I should mention, and I don't think I have it here, Sandro has been particularly successful at incorporating forces also. So Sandro is able to do molecular dynamics calculations. You do force calculations with QMC, and then you use that to do MD, noisy MD release. We can, if you're interested, we can talk about this, but effectively you can do molecular dynamics, for example. So we have been able to do Monte Carlo calculations of the ions for a very long time. David and Carlo have been the pioneers on this. In this case, you need to do calculation of energy differences, so that gives you one way to sample the ions. So you can do ab initio calculations completely on QMC. But Sandro has been very successful at taking the alternate approach, which is if you want to do molecular dynamics, you need a force. So he has spent a lot of effort in trying to get the forces out of Monte Carlo. You have statistical noise on the force, so you have to find a way to incorporate the noise on the force on the molecular dynamics framework. But this is pretty much a solved problem right now. And so he's able to do a lot of calculations that go beyond just ground states. He has polarizabilities, he has Raman spectra and infrared calculations and some very nice dipole moments and some very nice calculations on molecules. So if this is your field and you're interested in this, I strongly encourage you to look at their work. And so what's next? What's the outlook in the field? If you're interested in getting involved on the development, then there are many, many things where the field has to work on, so in order to become more widespread use and to become there are places where we certainly need some improvement. And so and this is all a personal perspective, of course. If you ask other people, they would have different answers, and it kind of depends on what you're interested in. But in my mind, what we have is the most important thing that we need right now is a more universal trial wave function in many ways. So something that's more flexible. I mean, we have the flexibility, but something that is more black box in some ways, that you would require less influence from external codes like games and quantum chemistry calculations, and even maybe a little bit more powerful ansatz. So all of these things are being worked on, by the way, but this is what I would think is the most important thing. So we want a better way to control the multi-determinant expansions. Right now, it's basically try to put as many determinants and to extrapolate to the infinite, to the limit where you put them all. But in practice, if we get a little bit smarter, very close to what Claudia is doing, we can probably come up with systematic ways of generating recipes that will give you more control over the multi-determinant expansions. And again, adding backflow has been shown to be a fantastic route. I did not put that here, but the ideas of Erik Nusskammer are very powerful, basically going into geminal type of wave functions, and then tailoring the Jastrow to remedy all the limitations that the geminal wave functions have. You can show that if you can do this, then you come up with a wave function that is extremely powerful. So we certainly need more estimators. This is again, this is a fairly old slide, you can tell. So 2 years ago, we were really thinking about this. Now, the work of Ray Clay, he's going to talk about this on Friday. So we have forces implemented. We also have second derivative. We want to go towards second derivatives, but we can do with forces, we can do quite a lot. So very soon, the code would have MD and Monte Carlo and geometry optimization and all of the algorithms that you need, where you need forces on. So this is mostly done. It's just a question of finishing the work and releasing it. But it would be released on a future distribution. Excitations, of course, is something that's important. Right now, there is a lot of work done by Claudia, but I think this is one of the areas where more work probably needs to be done. And of course, correlated systems. If you go to solids where there's a lot of correlation, if you want to do transition metal oxides or superconducting materials, then this is very much a research active area. There's a lot of ideas, but there's work that still needs to be done. So this is the areas where I think focus needs to happen. So if you guys are interested, of course, you're welcome to talk to any of us. And thank you for your attention. This is all I have. If you have any question about anything that I have said in the last today and yesterday.
Yeah, so you said that the forces are not implemented yet. So does it mean that when you're doing geometry on a new structure, you are getting the structure from the FT and building on the console?
Sorry, I'm being.
Can't hear me?
No, I'm being signaled and I don't quite. Oh, push the button. This is what he's saying. Sorry. Yeah. So that everybody can hear you. Yes, please. Yeah.
So you said that the forces are not implemented yet, and you are working on that?
So it's implemented, but it's not in the release version.
So when you're doing all those...
It might be, sorry.
Okay.
Anyway, sorry.
So in your calculations, then you are getting the initial structures from some kind of a DFT code,
yes,
and then building onto that?
Yes, for sure.
Okay.
Yeah. So the work in the forces is very advanced. I'm not quite sure how much of it is on the repository. But this is one of the more active areas that we have right now. So very soon you would have full force evaluation. And so where probably the forces are implemented is really developing the algorithms that use the force. So doing the geometry optimization, the MD drivers, all of these things, which it's just implementing things that are well known. It's just human time at this point. Yeah.
You have some smart way to solve forces like Ham-FM theorem, or you just solve it numerically?
Can you say that again? Sorry.
I mean, for solving forces, you have some smart way like Ham-FM theorem, or? So
this is just drawing on what the community has done. There are two standard ways of getting forces: the separately Chieta algorithm, which smooths basically tries to remove the diverging components of the force. There are issues with noise when you calculate forces, and we can go into detail if you want. I think Ray might be talking about that in some detail on Friday. But there's some technical things that have to be dealt with to reduce the noise on the force calculation. And so we're using what will be implemented are the standard method that the community has agreed upon. There are two of them. There's one, again, done by separately, which that one is implemented and works very well. We're working on finishing the implementation on the one that Claudia uses. So there are a handful of people. I don't want to remove the I think Claudia is probably the best known person, but Cyrus, Sandro, Saverio Moroni, they have come up with an alternative way, which is very, very powerful, and we're working on implementing that. But it's in a sense, this is what the community has converged on, I would say. Yeah.
How about spin orbit coupling?
So right now, this is not in QMC pack. So he asks about spin orbit coupling. This is not in QMC pack. In the real space version, it will be in orbital space and an orbital space extension that will be released from the code very soon. But if you want to do real space spin orbit coupling, the Lubos Mitas is the person working on that, and so it might be in the code in the future. But as of right now, it's not currently implemented. This is still very much a research problem, and it's not clear exactly what the best way to do spin orbit coupling is. So when the problem gets solved, or I mean, when better progress is made, this is very, very new, by the way. There are only like a handful of papers on the topic. So it will be on the code as soon as we have a better resolution of what the optimal approach is.
Yeah, I just wanted to make the same comment. So spin orbit is very much a research topic, and Professor Lubos Mitas at North Carolina State University is probably the main person pushing this currently, so look for papers there now. And of course, there are many choices that can be done here, and when it's clear what the right thing is, or the best thing, we'll put that in, or maybe someone else does some development work in that area, and there's a competitor, and we end up with two methods. But certainly, it's a research topic right now, and so you can see calculations on atoms, for example, that have been done, and it looks very promising. But as Miguel said at the start, there's only so many people working on this area, so things take a little while to develop.
Right. Any other question? Yeah.
Can you talk about the started electron interaction?
It will be soon. Depends on what you mean by it. So he asked about electron phonon interaction. Depends on what you mean by that. Of course, this means different things to different people. But there will be a way to extract phonon information from the code by finite differences implemented in some future version. This is something we're currently working on right now. As of right now, it's not in the release version. Yeah. Okay.